These are the five main reaction types we can identify for a chemical reaction equation. A synthesis reaction is where we put together simpler substances to make one product. Now, what those simple substances are, whether they are pure elements or just small molecules made of several atoms, doesn't make a huge difference. The one thing that matters for a synthesis reaction is you must make only one product. So on the right side of the arrow, you should just have one chemical formula, not plus something else. A decomposition reaction is kind of like the opposite of that, where we go from having one reactant that breaks apart into multiple substances. That could be pure elements or it could be just other molecules. But the big thing here is that a decomposition reaction cannot have more than one reactant. It's just got to be one chemical formula on the left side of the arrow, and then no plus anything else. A combustion reaction is one of the most specific types of reaction because you specifically need to have something with carbon and hydrogen, sometimes oxygen, reacting with O2 to make CO2 and H2O, carbon dioxide and water. If you do not have those specific things, it cannot technically be a combustion reaction, which means you might see a reaction that gives off flames and heat and light, but if it's not making CO2 and H2O as your products, it's not technically a combustion reaction. A single replacement reaction is a reaction where we have a pure element switch places into a compound to kick something out of that chemical formula, and the thing that gets kicked out ends up on its own as a pure element. So we should have one pure element and one compound, and we do a little switching where the element ends up in the compound and the thing it takes the place of is now out on its own. A double replacement is similar to that, except we don't have a pure element in either case on the reactants or the product side, on the left or the right. We just have two compounds that switch partners. So it looks like you've got two things stuck together plus two things stuck together, and then the arrow happens, and on the right side of the reaction equation, you've got some things that have switched places. Either the first part of the chemical formula has switched places, or the second part has switched places.
This jar is full of hydrogen gas, and I want it to react with oxygen gas, which is already in the air around outside it. The extra hydrogen gas is bubbling up around here. And to show that it's hydrogen and not just regular old air bubbles or something, I can light them. If I give them a little bit of a push, the reaction that happens is the combination of hydrogen gas and oxygen gas to make water. Okay, I'm going to lift the jar, and then as the oxygen comes in contact with the hydrogen inside the jar, I'm going to give it a little bit of a nudge to start the reaction using the heat from this lighter. Here we go.
In this reaction, elemental hydrogen H2 and elemental oxygen O2 react to form our single product H2O, that's water. Since we only make one product in this reaction, this must be a synthesis reaction. The way that we balance a chemical reaction equation doesn't really have anything to do with the reaction type. The way that you balance an equation happens the same no matter what you're looking at. As long as you have the same number of atoms on both the left and the right side of the arrow, then everything is accounted for, and therefore the reaction equation is balanced. So in this case, we're starting with two hydrogens on the left and two hydrogens on the right. On the left, we have two oxygens, and on the right, we only have one oxygen. So we're coming up a little bit short in the oxygen side. Now, the only thing that can give me more oxygen on the right side, on the product side, is my H2O. So I would need to have two H2Os to get two oxygens on the right side. Now, if I double my H2O, that means I'm also going to have twice as many H's as I had before. So I'm going to end up with 4 hydrogens and 2 oxygens. In order to fix that, I've got to look at the left side, where I now don't have enough hydrogen. If I have two H2s instead of just one, then that would give me 4 hydrogens and 2 oxygens on the left side to match the 4 hydrogens and 2 oxygens on the right side. Anything I don't have to change can be used as a 1 for my coefficient. So 2 H2s plus 1 O2 should be able to make 2 H2Os. This reaction uses only one reactant, mercury 2 oxide, and unfortunately I don't have any of that in my lab, so I'm borrowing this video, and the link is down at the bottom. In this reaction, we apply some heat to this mercury 2 oxide, this orange powder, and as it heats up, it goes through a reaction where it breaks apart into mercury metal, Hg, and oxygen gas, O2. Although you can't really see the oxygen gas on its own, you can see the mercury being formed as that darkish colored stuff, and you even sort of get this metallic coating on the inside of the test tube. You can check for oxygen by lighting a splint, blowing it out, and having it relight in the presence of lots of oxygen that's in the test tube, or that you can collect underwater in like this graduated cylinder that's being shown here. Since mercury 2 oxide, or HgO, is the only reactant in this reaction that breaks down into Hg and O2, this must be a decomposition reaction, since we only have one reactant breaking into simpler substances in the products. At first glance, this reaction equation looks almost balanced already. We have one Hg on the left and one Hg on the right, so I'm not going to mess with those for now. But I only have one oxygen on the left compared to the 2 on the right. So I'm going to need to get more oxygen with the only thing that's giving me oxygen on the left side, which is the HgO, which means I'm also going to get a little bit more Hg. This is a common problem you'll find in questions like this. When you're trying to balance chemical equations, sometimes you have to mess up things that are already balanced in order to get to a place where you can balance everything. And that's okay. It's a trial and error process. It takes some problem solving. So once we have 2 HgOs on the left side, we now have enough oxygens to match, but we need to fix the number of Hgs on the right to match. So I just need to make the coefficient in front of the Hg a 2, so we have 2 Hgs and 2 Os on both sides.
This reaction is going to take place between methane, CH4, carbon tetrahydride, and oxygen gas. Since I already kind of showed this with the Bunsen burner, I thought I'd do a different version this time. I'm going to run some gas through some soapy water down here to catch some bubbles of methane gas. Okay. Now that the methane gas is trapped, I can give it a little bit of a light, give it a push, so that the oxygen in the air can react with the methane, and we get a flame. Now here's a trick you don't try at home. As long as you keep your hand wet, you can kind of protect yourself from some of the heat of the flames. So if I scoop up some of these bubbles and I light them, I don't get hurt. Okay? But again, you should only see that as a demonstration. You should not try that yourself.
At first glance, this reaction equation kind of looks like a single replacement reaction, since we have a compound and a pure element on the left side. But on the right side, we don't have a compound and a different pure element, like that pure element kicked something out. The oxygen does wind up with the carbon, but we don't end up with pure H2. We have H2O, which is also still a compound. So this can't really be a single replacement. Instead, this is a combustion reaction, where something with C's and H's reacts with O2 to specifically make CO2 and H2O. Even if you have a different compound of C's and H's, like C3H8 or C4H10 or C6H12O6, as long as it reacts with O2, you're going to make some number of CO2s and H2Os. From there, we can just balance it by changing the coefficients out front. So on the left side, we have one carbon, and on the right side, we have one carbon, so that checks out. But both our hydrogens and our oxygens don't match, which means we gotta work some things out. Now, it doesn't really matter which one we start with, although in problems like this, I would recommend starting with carbon, then hydrogen, then oxygen. So since our carbons are already matching, we're going to go to hydrogen next. I need to have 4 hydrogens on the right side to match the 4 I have on the left. So the place I'm getting H from is H2O on the right side. So I'm going to double that. If I have 2 H2Os, that would give me 4 H's. It's also going to give me another oxygen. So now on the right side, I have 1 C, 4 H's, and 4 O's. That's closer, but on the left side, I'm still missing 2 O's. So I need to get another 2 O's by looking at that O2. If I had 2 O2's, that would give me 4 O's on the left side to match the 4 on the right. Then everything is balanced. From there, I just need to have a coefficient of 1 for everything I didn't have to change.
In this reaction, I'm going to add some zinc metal into this hydrochloric acid down here. Drop this in there. I'm going to start bubbling and fizzing. And the atoms are going to rearrange to make 2 main things. One of them is going to be zinc chloride, and the other, where you see the bubbles coming out there, is hydrogen gas. This is the reaction I used to make the hydrogen gas for our synthesis reaction earlier. You might be able to see that the zinc is taking on this darker color. That black color of the zinc pieces is coming from one of the products that we're making this reaction, which is the zinc chloride. That original zinc metal is rearranging and sticking to atoms of the chlorine from the hydrochloric acid in here. So the black stuff is zinc chloride that we're making, and then the bubbles coming off are the hydrogen gas.
Here we have zinc as an element reacting with HCl, that's hydrochloric acid or hydrogen monochloride, forming zinc chloride, this ZnCl2, and H2. Now on the left side we have a pure element and a compound. On the right side we have a compound and a pure element. Even though our H2 is not a single atom, it is the only element there. Plus H2 means plus just an element. So this must be a single replacement reaction, since we end up with a pure element on both sides of the reaction equation, and one of them forces its way into the compound to kick something else out. In this case, the zinc takes the place of the hydrogen, which gets left out on its own. This reaction equation looks pretty complicated, but it might actually not be as hard to balance as it would seem just at a first glance. I'm already balanced with my zinc on the left and the right side, since I have one on the reactants and one on the product side. I need to have 2 H's and 2 Cl's on the left side to match the right side. And thankfully, both of those things are together on the reactant side as HCl. If I just change the coefficient to 2 in front of the HCl, that'll give me 2 H's and 2 Cl's on the left side to match the 2 on the right side. And that's all I have to do. Then everything else is balanced. I can put a 1 as a coefficient in front of everything else, so I keep the balancing the same, and then we're done.
Concentrated chemicals like acids and bases can be harmful to you, which is why you have to be careful and use precautions like gloves and goggles in the lab. Here I have concentrated sodium hydroxide and concentrated hydrochloric acid. And I don't really remember which one is which, because they look pretty much the same, and both of them look pretty much like water. Since they're dissolved in water, they don't take on any other specific characteristics, so by sight, they don't look any different than regular water, which can make them dangerous. You should assume that everything in the lab is not safe to get on your hands or drink for reasons like this. Now, to show that there's a reaction between these two, I've got a thermometer in this glass, because I'm going to combine them together. And one of the signs that a chemical reaction is happening is that there is a change in temperature to show that heat is being exchanged. Heat's moving from one place to another. But other than that, they kind of started looking like water and they end looking like water. To show how acid-base reactions happen, we sometimes use indicators. Chemical indicators indicate whether a chemical is acidic or basic. And I want to show you one of those indicators. The acid-base indicator I'm going to use here is phenolphthalein. Really hard to spell. And it looks just like water, just like the hydrochloric acid and the sodium hydroxide. I'm going to add some into this beaker. And again, doesn't really look like much is going on here. What phenolphthalein does is it changes color depending on whether there is an acid or a base present. Specifically, it goes from colorless to pink when there's a base around. Yeah, a little bit more in here. However, if I have a chemical reaction between sodium hydroxide and hydrochloric acid, where they change into something else, you'll notice that pink color is starting to go away. And then it's gone. The products of this reaction are salt and water, where the salt stays dissolved in the water. So if I have a little bit of extra sodium hydroxide in here, you can see it changes pink because the phenolphthalein is still in there. But as it reacts with the hydrochloric acid and changes into something else that's not basic, it's no longer pink anymore. It goes back to being colorless.
There's a lot going on in this reaction equation. We have HCl, that's hydrochloric acid or hydrogen monochloride, reacting with sodium hydroxide, NaOH, to make H2O, which is water, and NaCl, which is sodium chloride or table salt. We essentially have a compound plus a compound makes a different compound plus another different compound. And although there doesn't seem to be any connection at first glance here, if you imagine splitting those two compounds on the left in half, the H and the Cl, and the Na and the OH, where the OH kind of sticks together. If we switch places with the Cl and the OH, we'll get HOH and NaCl. Now, HOH is two hydrogens and one oxygen. It's H2O, just a different way of writing it. And NaCl is the other product we have over there. We essentially have a switching of places with two things, which makes this a double replacement reaction. Like the example before this, sometimes a reaction equation can look really scary, but it actually isn't all that hard to balance. Sometimes you don't actually even need to do anything to balance a reaction equation. If we check the left versus the right side, in total we have one H in the HCl and one H in the NaOH. That's two H's on the left side. On the right side, we have our two H's from H2O. On the left side, we have one chlorine. On the right side, we have one chlorine. The left side has one Na, the right side has one Na. The left side has one O, and the right side has one O. Everything here is accounted for. You can start with one HCl and one NaOH and make one H2O and one NaCl. You don't actually have to change the balancing on this one. It's okay if all of the coefficients end up being 1. Sometimes it's just that simple.